the same energy and get big. And that's apparently what these reptiles were doing. Everything was a giant. In general, bigger is better. You're better at competing for mates. You can kind of shove the 80-pound weakling out of the way, or you can eat larger things, and it takes larger things to eat you. So there's just a lot of advantages in being big. One of the advantages is you simply get to places faster, because if your legs are short, you're just simply slower.
Experts can reconstruct an animal's long-lost environment by analyzing the content of the soil it walked on.
As a paleontologist, I've worked in Egypt and in the Gobi Desert of China and in Patagonia, but I also come right here to New Jersey, right here to this pit that contains sediment that was deposited about 65 million years ago at the very end of the Cretaceous period, at the end of the time of the dinosaurs.
Professor Lacovera and graduate student Jason Shine investigate the mineral composition of the soil in this mining pit. It gives them their first clue to what this spot once was: beachfront property.
So the dark green color of this sediment is caused by the mineral composition of this deposit. The mineral that's giving it this color is called glauconite. And glauconite almost always forms in a shallow, productive marine environment. The seafloor was occupied by just a plethora of different marine animals, invertebrates and vertebrates. They were walking on the surface, they were digging down into the ground, and they were disturbing the sediment as it was being deposited. That's a process that we call bioturbation. But what we see here is evidence of just a riot of life that was going on at this location.
Just a little looking supports this observation. It's a productive fossil site.
And here is a vertebra of, I'm guessing, crocodile.
We've been here for 5 minutes, and already we've started to discover 65-million-year-old crocodiles right here in New Jersey.
Experts are able to look at an environment today and figure out what happened in the distant past.
It's sort of like CSI. A good sediment geologist is a very sophisticated detective. They have a lot of tools at their disposal, from microscopes to mass spectrometers, and they can find a lot about a sediment environment by using those tools appropriately.
If we watch waves today on a beach, or if we watch a river flowing down a valley, we can see the processes operating there, and we can see that they leave a signature in the sediments that allow us to fingerprint an environment. This sediment here is ancient, but it's unconsolidated, unlithified, as we say. It could also be the case that groundwater going through this sediment could precipitate out minerals between the grains, cement them together, and this could become a sandstone. That sandstone could be thrust up into a mountain range, and still, it would have the fingerprints of its deposition, and we would be able to go up into that mountain range and say, oh, shallow marine deposit near a coast. The present is the key to the past.
And just as understanding an animal's environment leads to deductions about its life, analysis of a creature's bones can tell us about its environment.
We look at specific details of the chemical composition of their bones and the specific isotopes of certain elements like oxygen and carbon that are trapped in their bones. They tell us a tremendous amount about what they ate and what the climate was like. And so there's lots of ways you can now narrow down a lot of older ideas about animals and say, okay, these things are now reasonable, these things we've ruled out.
Yesterday's ideas about dinosaurs are constantly changing based on new environmental work. For example, the profile of Spinosaurus, a 7-ton megacarnivore from the Cretaceous period in Africa, has recently been revised.
You might have seen portrayals of Spinosaurus as being this really gung-ho predator that might jump on the backs of other dinosaurs, etc. Well, we know now from environmental work that Spinosaurus lived in a mangrove swamp about 95 million years ago, and it probably ate fish. And in fact, it had 6-foot spines coming off of its vertebra that don't appear to have been flexible. It probably would have been a fairly cautious animal as opposed to sort of a cartoonish version of it. So if you don't understand the environment of that animal, you really don't understand the animal.
The more bizarre the creature, the harder it may be for scientists to truly understand behavior. Using CT scans, scientists venture inside the giant heads of these lethal predators. At the dawn of the Cenozoic era, a new South American super predator stepped in to fill the vacancy atop the food chain caused by the extinction of the dinosaurs. Starting 58 million years ago, the Forus racidae, who reached heights of 9 feet, chased down prey at speeds of up to 30 miles per hour. They have been nicknamed terror birds for their fierceness.
We can sort of look at the terror birds and we can sort of see in them almost a re-evolution of many of the attributes that we see in some of these more conventional predatory dinosaurs. Terror birds aren't quite as big as Tyrannosaurus, but they're still, for birds, gigantic, bipedal animals running around on 2 legs, but then also very much head dominant, pushing 3 feet in length. That's an enormous, ridiculously large skull. These animals were probably very much Tyrannosaur-like, using their heads more than other parts of their anatomy as the killing and manipulating organ.
But curiously, this family of birds gave up flight and returned to the ground.
Yet it does seem really counterintuitive to evolve this mode of locomotion that seems so wonderful, flight, to actually get rid of it and become flightless.
Researchers speculate that terror birds gave up flight because it allowed them to develop large, reinforced skulls suited for capturing and dismembering animals, but too heavy for flight.
They have really, really huge heads for any bird. And most of that head is this big, long, very deep, very sharp beak with a big hook on the end. You don't see that except in birds that are predatory. There's no reason for a non-predator bird to have a big, sharp hook at the end. And especially a skull that size, with a beak that rigid and that robust, it only makes sense if they're cutting and breaking very large things, large cuts of meat.
The skull of Andogolornis, a 5-foot-tall terror bird that lived 5 million years ago, illustrates the stark difference between birds that can fly and those who can't.
And we can see that it's actually set up quite a bit different from some of the other skulls that we can see in this area here. For instance, this right here is the skull of an 8-foot-tall ostrich, and this is the skull of maybe a 5-foot-tall terror bird. We can see this is dramatically different than what we see in this ostrich.
The Andogolornis skull also dramatically differs in structure.
In front view, you can really get a sense of how narrow the snout is. So they have a very tall, very narrow snout, which has a big impact on the function or the biomechanics, really the architecture of how these skulls are built. What that suggests is that this skull is really built for, in a sense, biting down, and also for tearing, pulling back. So this hooked beak right here, which would be covered in a horny substance, would actually dig into the prey, then the neck would pull back and retract the entire skull, which would impart sort of a ripping or tearing movement. What's really interesting is if we actually CAT scan this guy, get inside and really see how he's constructed. What we'll do is we'll scan it pretty much in life position here.
At Oblenis Memorial Hospital in Athens, Ohio, Chief CT Technologist Heather Rockhold helps Dr. Whitmer prepare to scan.
All set?
Yep.
All right, let's go have a look.
Okay.
When we use something like CT scanning to look inside the skull of an extinct animal, what we see are basically the bones and the spaces within the bones and around the bones. The brain is long gone. Time has stripped that away. However, what we can do is still look at what the brain cavity tells us. And the brain cavity itself records the general shape of the brain. Huh, that's interesting. Here in the back part of the brain, so this must be the cerebellar region in there. What we see there is that the cerebrum is actually quite large and has large visual sensory areas within the cerebrum.
These attributes indicate to experts that detecting odors was not that important for terror birds.
That's interesting. It's sort of
Though these animals would not have turned down a malodorous scavenged meal, they primarily hunted down live prey.
the delicate canals of the inner ear, which are buried deep inside here. What those show us is that this two-part function of the inner ear, the one function associated with equilibrium or the sense of balance, the other with hearing, both of those are very well developed, suggesting that balance and sensing turning movements of the head, which is what the top part of the inner ear does, was very sophisticated in this animal. This animal actually was able to sense subtle turning movements of the head and probably employed relatively rapid and quick turning movements to keep its eyes fixed on potentially fast-moving prey. Now we're getting up into the beak.
The CT scan of the snout reveals something unexpected.
That's interesting. It's like a cavity in the beak there.
It's totally hollow.
Given the lifestyle of this animal as a predator and how narrow it is, we would have predicted that this hollow space would have been buttressed internally by struts. We don't see that. That cried out for explanation. In fact, that explanation was kind of long coming because it had us really surprised.
Scientists now speculate that Andogolornis clapped its jaws together to create a low-frequency sound.
Low-frequency sounds have the interesting property is that they can propagate over long distances, even sort of over rough or heavily forested terrain. Certainly, this sort of chattering of the jaws with this deep wooden resonating chamber in the snout could have been important for courtship, but it also could have been important for communication over long distances. These are not the kind of things that we can answer for sure, but one interesting thing is that the CT scanning actually raised this whole issue altogether.
The CT scans also indicated something scientists never thought they could predict: the posture of these prehistoric animals when they were wary. There was a clue to this locked deep inside their skulls.
When animals are alert, like when a twig snaps, they tend to orient their head in a very characteristic posture. And it turns out that that posture is in such a position that a particular part of the inner ear is oriented horizontally, level with the horizon. In reality, animals spend a lot of time being alert. And so the fact of the matter is we can now reconstruct the alert posture of these animals. For instance, for some of these pterosaurs, it turns out that some of them held their heads horizontally when they were alert. But others, it turns out that they actually held their heads strongly nose down, that their heads were very steeply inclined when they were alert. Kind of makes sense, because what it means then, if we put it in this orientation and look at it in head view, this crest right here actually will sort of block the vision. By dropping the head down, it'll actually allows vision to be much more enhanced, and actually visual field overlap, which enhances binocular vision.
Though CT scanning allows scientists to reconstruct the brains of extinct animals, they still turn to modern animals to attempt to reconstruct fine details, like the way flesh interacts with bone.
We've always looked at the skulls of these dinosaurs and seen holes and grooves and things like that. And for a long time, they didn't seem to really carry much significance to us. We knew that maybe there was probably blood vessels and nerves, but we couldn't really make any sense of that. What really allowed us to sort of put the pieces together, we're actually looking at the modern relatives of these animals.
Dr. Whitmer dissects modern specimens in an effort to reconstruct the soft tissues of the dinosaurs.
We're really trying to sort of flesh things out and see what these animals were like. We really need to look at animals that are around today that still have those soft tissues that we're trying to reconstruct in the dinosaurs. Fortunately, we've got some resources right here. Got a walk-in freezer with all kinds of critters in it. And we really have a whole host of animals in here. Everything ranging from crocodiles to rhinos. We've got loons. but we'll actually probe these animals, strip off the flesh literally to see how it interacts with the bone. Then we'll take that information, go back to the fossils, and really start to sort things